It is interesting that one of the most famous paradoxes, the Fermi Paradox, in a way is neither a paradox nor it is Fermi's. The paradox is named after the renowned physicist who was awarded the Nobel Prize in Physics, Enrico Fermi. However, Fermi himself never officially published any works on this so-called paradox, and it wasn't part of any of his conference presentations. The paradox is named after him because of a question Fermi supposedly asked during a lunch conversation around 1950. The discussion involved flying saucers and interstellar travel. He asked, "Where is everybody?" referring to the aliens that we haven't seen. This story is more like a legend. It wasn't documented in any way and is known to us only from the accounts of those who were part of the conversation. And even they said that they only partially remember it. However, there were also actual papers that discussed this issue, now known as the Fermi Paradox. If there are so many planets in our galaxy and some of them could be habitable, possibly even hosting intelligent life, why don't we see life anywhere other than on Earth? It is often noted that life on Earth has existed for about 4 billion years, while the lifetime of our human civilization is just a tiny fraction of that time. If a civilization emerged much earlier than ours, it could have already colonized the entire galaxy by now. Yet we don't see anyone anywhere. That's the paradox. Again, none of this was published by Fermi himself. Similar idea, for instance, is found in a 1975 paper by Michael Hart, that even with only subluminal spacecraft, a highly advanced civilization carrying out a full-scale expansion could relatively quickly conquer the galaxy. At 10% of the speed of light without stopping, it could accomplish this in about 650,000 years. With more conservative estimates of a few million years, which is still very little in the scale of the universe's lifespan. In other words, for a civilization in the universe that is 13.8 billion years old, it would only need to have reached such a level of development only a few million years ago to have already been here, but we never see them. Furthermore, actually we shouldn't even call it a paradox. The term usually refers to a situation where contradictory or mutually exclusive statements arise. However, the fact that we currently don't see anyone else is not a 100% guarantee that there is no one else. The presumed prevalence of conditions suitable for life does not guarantee the emergence of life, and especially highly advanced civilizations that would also be capable of colonizing the entire galaxy. Between these two options, there is a whole range of possibilities, which is addressed by numerous existing solutions to the Fermi Paradox. I'll still call it that. Yes, there are indeed many solutions, although they can be grouped into a few main categories. But today I want to talk not about the paradox itself. This topic is very popular and there are already a plethora of books, articles and videos about it. But the problem still preoccupies scientists, and new solutions or new versions of existing solutions continue to emerge. Papers on that topic continue to come out, and today I'll tell you about some of them. What is the contact era and when will we reach it? How can we use the focal point to contact extraterrestrials? What is the silent bubble and the Galactic K-dwarf club? Today we'll discuss all this and more. I'm Andrei, and this is Cosmos Elementary. So, existing solutions to the Fermi Paradox attempt to explain the fact that we have yet to see anyone else in the universe. I won't list all of the existing solutions, as today we are focusing on the more recent ones. But briefly, first of all, it might turn out that there is no paradox at all, and we don't see anyone simply because there is no one else to see. In this context, you might have heard about the rare Earth hypothesis. A lot of factors had to align on our planet for life not only to originate but also to persist for billions of years, evolving to its current state. There are so many factors, and the values of some variables are so sensitive to change that it seems that the emergence of intelligent life is an extremely unlikely event. It might be that not just the emergence of intelligent civilizations is unlikely, but the origin of life itself could be improbable, and many factors influence this as well. Recently, a number of interesting studies were published that took these factors into account. For example, not only the presence of water, but the existence of continents, and most importantly, plate tectonics may be crucial. According to the authors of this paper, the presence of these two conditions could be very rare, which significantly reduces the potential number of habitable planets. In addition to the usual habitable zone, the authors of this article also considered the so-called ultraviolet habitable zone. And this study also accounted for the influence of the magnetic field and not of the planet but of the star. And another study even considered the shape of orbits. There may be many more such factors which together make the emergence of life very unlikely. In its own way, this could resolve the Fermi Paradox. Other solutions allow for the existence of other civilizations but try to explain why we still cannot see them. A well-known generalized explanation is a so-called great filter. As I've said, many factors must align for a galactic civilization to emerge, which is considered unlikely. There might be some barrier or barriers that prevent life or civilizations from reaching a level of development where they would be capable of colonizing the galaxy. These barriers could be external and independent of the civilization itself, such as global catastrophes, asteroid impacts, nearby supernova explosions, and so on. Alternatively, the civilization itself could be responsible for such a catastrophe, effectively causing its own self-destruction, which is, looking at our civilization, not hard to believe. There's also a simulation hypothesis suggesting that we might be living in a simulation, and I recently discussed this in a separate video. The zoo hypothesis suggests that extraterrestrial civilizations exist, are aware of our existence, but do not reveal themselves or interfere in our lives, possibly only observing us. Or perhaps we've just searched not hard enough, which is indeed a possibility. Or maybe aliens are so different that we wouldn't recognize them even if we did see them. Or what if it never occurred to them to make contact or colonize the galaxy? Maybe they are deliberately hiding, and so on and so forth. All the recent ideas we'll discuss further stem from the assumption that other intelligent civilizations may exist and specifically address why we still do not see or hear them. Therefore, it is important to make a crucial disclaimer. Given that this is quite a significant assumption, all these ideas, while interesting and may even sound reasonable and are based on some real facts and data, these are still speculations. Let's return to the point that a highly advanced civilization capable of expansion could colonize the galaxy even with subliminal spacecraft in just a few million years. According to this logic, we should be seeing them everywhere. Or perhaps we have already seen. Let's assume they do exist, but we know nothing about them or their motivation. Let's say they started colonizing the galaxy for some reason. Firstly, it is not at all certain that this colonization would proceed continuously without stops. Therefore, the optimistic estimate of a few million years could extend significantly. But a truly important aspect is motivation. Sure, the population may grow and the energy needs may increase. An interesting option is discussed in this paper. This study assumes that life can only originate and persist long enough to reach a technological phase around stars similar to our Sun, such as K-dwarfs. These stars have long lifespans, longer than more massive stars, and are not as dim or as active as red M-dwarfs. Although the lifespan of K-dwarfs is relatively long, about 10 billion years, this may still be insufficient. Additionally, it's not guaranteed that the planet where life originated will remain habitable for the entire duration of those 10 billion years. Due to the fact that our Sun is slowly becoming brighter, Earth could become uninhabitable in about 1.5 billion years. Therefore, if a civilization simply wants to survive, it may try to find a new home beyond its original star system. K-dwarfs are good candidates for this purpose. Depending on their mass, they can live from 17 to 70 billion years, which is significantly longer than K-dwarfs. At the same time, the conditions in such systems might be close to those in systems with Sun-like stars. M-dwarfs, although more common, are often much more active, especially when they're very young. They can be hazardous to life due to powerful frequent flares. Additionally, they are dimmer, so their habitable zones are closer to the star, which can lead to tidal locking of planets and result in less pleasant climatic conditions. K-dwarfs turned out to be a sort of Goldilocks zone. They make up 13% of the stars in our galaxy, but habitable planets may not be present in every system. One can imagine a scenario where a civilization is fortunate to be near such a system and would wait as long as needed for it to come closer, reducing the distance they need to travel with subliminal spacecraft. It is clear that such a scenario of galactic expansion would take much longer. If a civilization continues to colonize the galaxy using K-dwarfs, it could take billions of years. This concept is referred to as a K-dwarf galactic club. So by this logic, it is not necessary that aliens should be everywhere. They would be found only around specific stars, and our system might not be of interest to them at all. Thus, we don't see anyone. This could be a potential solution to the Fermi Paradox. Interestingly, this paper not only proposes such a solution, but also suggests potential targets for future searches for biosignatures and technosignatures. It advocates focusing specifically on the study of planets around K-dwarfs. It is also possible that we haven't yet entered the contact era. Extraterrestrials might not be sending us ships, probes, or even signals simply because we are not of interest to them. This is discussed in the paper by Amory Wendell, and not in the sense that we are like insects to them. They might know about our planet, perhaps even know that it could harbor life, or that there is life on it, but they might not be aware that there is a relatively advanced civilization here. For the argument in this article to hold, a few assumptions need to be made, besides the main one that advanced civilizations exist. Firstly, it must be assumed that while life in general is fairly widespread in the universe, it is not so for advanced civilizations. There are many habitable planets in our galaxy, but intelligent life is a rare phenomenon. The second assumption is that the resources of the supposed alien civilizations are limited, which is a fairly reasonable assumption. If they have discovered many habitable planets, sending a ship or even a probe to each one of them in search of intelligent civilizations would be very wasteful. They would probably select targets that stand out from the general population. For instance, in addition to biosignatures, they might look for technosignatures that indicate the presence of a technological civilization. The thing is, it's quite likely that Earth would not appear as such a target to them. There is an interesting concept of the radio sphere. The essence is that we started actively sending artificial radio signals about 100 years ago. Given the limitation of the speed of light, the farthest our signals could have traveled is 100 light years from our system. This means that we're living within a sphere with a radius of 100 light years, inside which, if there are any extraterrestrials, they could potentially have intercepted our signals and learned about our existence. Within this sphere, we know of about 15,000 stars. However, considering that we would also need to receive a response to confirm that someone is out there, the effective sphere is halved, resulting in a radius of 50 light years. This reduces the number of systems to around 1,300. This is out of several 100 billion stars in our galaxy. What are the chances that an intelligent civilization will be so close? Worse still, most of the signals we send are very weak and might be indistinguishable from the background noise. Therefore, the effective sphere might be even smaller. The smaller our radius sphere, the lower the chance that anyone will learn about us at this moment. And what if a civilization were 1,000 light years away? It could easily be the case that, assuming there is plenty of life in the galaxy, they might not find our planet interesting. Life on our planet has existed for billions of years, and biosignatures could potentially be detected from any corner of the galaxy. However, technosignatures can only be detected from a very small bubble in close proximity to Earth, and we may need to wait a long time, possibly thousands of years, for our signals to travel far enough for us to enter this so-called contact era. At that point, we might be heard, become interesting, and then someone or something might come to us. And until then, so this might be the solution to the Fermi Paradox. Now let's talk about the silent bubble scenario. As part of SETI programs, humanity has been trying to detect signals from extraterrestrial civilizations for 60 years, and so far with no results. Occasionally, interesting signals are detected, but they are always found to have either a natural explanation, such as signals from astrophysical processes, or are simply terrestrial interference, like signals from a microwave. The famous WOW signal has been one exception, and it has not been explained with 100% certainty. A new paper has just come out suggesting that the source for this signal is an astrophysical maser flare. However, given that it has not been detected again, it might never be fully explained with 100% certainty. But it is unlikely to be from aliens. Again, the simple answer to why we haven't found anything in 60 years is that there is no one out there, and there is nothing to find. However, the question can be framed a bit differently. We've only been searching for 60 years. And indeed, on the scale of the galaxy, this is a very short period. We have only surveyed a very small portion of the galaxy with radio telescopes. What if our equipment is simply not advanced or sensitive enough? And also, what if we simply missed the signal? It might have come from an area we weren't listening to at that time. This paper develops the logic further. What if there are signals from extraterrestrial civilization that we could potentially catch, but they're simply very rare? And there is a long time between events when an alien signal hits our planet. And since we began to actively scan space, no such signal has arrived, and we are still in a silent bubble. The author of this paper built on this idea and used Bayesian statistics to estimate the chances that no signals from another civilization have reached Earth in 60 years. And it turns out that the chance of this is quite high. One of the conclusions of the study is that, assuming signals are rare, even if we scan the entire sky and not just listen to individual systems, but do so continuously without interruptions, we might not detect anything for hundreds or even thousands of years. The shorter the period of observation, the lower the probability. The study suggests that the chance of catching a signal over 240 years is 20%. For 60 years, it is much lower. However, according to the calculations in the article, the chance of detecting a signal within 100,000 years is 95%. In summary, we just need to be patient. Obviously, these are just statistical calculations and do not provide any information about the actual existence or non-existence of other civilizations. However, the next study, besides proposing another solution to the paradox, also explains why signals might be rare and describes a method to improve our search efforts. It is possible that we haven't caught anything from aliens yet because they are waiting for a special moment. Not related to our development, but rather a moment when the chance of us actually detecting the signal would be higher. The galaxy is huge, and if another civilization wants to send us a signal, they might assume that we cannot continuously monitor billions of stars. Therefore, to increase the chances of their signal being received, they might try to find the most suitable place and time. Here, the authors of this paper use the concept of a Schelling point, or a focal point. This is the idea that when, for example, two people cannot communicate with each other, they both choose a default strategy to solve a problem. Here's an example. If two people need to meet in the city on a particular day, but they cannot contact each other for some reason, they need to choose the place and the time where and when the chance of actually meeting will be higher. In most cities and towns, there is likely some sort of a traditional meeting spot. In the city where I was born, we used to say, "Let's meet by the clock," which is situated in the city center. So it makes the most sense for both of them to go to such a place and to choose not a random time, but let's say noon. That would be our Schelling point. If you survey a large number of people on how they would behave in such a situation, a significant percentage would likely choose that strategy, thus increasing the chances of meeting. In our case, these two are us and the aliens, and the city is the galaxy. However, instead of meeting, we're talking about a signal. The question is, what Schelling point can we choose in this scenario to increase the chances of detecting such a signal? The study suggests using planetary transits as the Schelling point. This situation occurs when, from a certain perspective, a distant observer sees a planet passing in front of a star. Currently, this is the main tool for finding exoplanets, but why not use it for communication? The thing is that the transit of a specific planet is observable only from a particular angle. The system needs to be positioned in such a way that, from our point of view, the planet crosses in front of the star. Secondly, transits have a clear and predictable period. And importantly, both we on Earth and potential aliens wishing to send us a signal can calculate when and where a transit will occur. Let's suppose a highly advanced civilization has learned about our existence, and it so happens that we on Earth can observe a transit from their planet passing in front of their star. Or perhaps they're so advanced that they have conquered many systems and have the luxury to choose which system to send a signal from. Among the systems they have conquered, there are some where the transit of their planets can be observed from Earth. Since they know that from our planet we can observe the transit of their planet across their star, instead of sending the signal continuously or randomly, they might choose to send a signal when their planet is aligned with their star and our planet. And both we and they can predict and calculate such an event. This would be a kind of a Schelling point and the best time to point our telescopes at exoplanets. By considering this possibility, we can not only choose specific planets and systems, such as potentially habitable ones around Sun-like stars or K-dwarfs, as targets for our searches for signals, we should also listen during the times of planetary transits. And we haven't detected anything so far because we haven't used such a strategy. Moreover, it's clear that it wouldn't necessarily work immediately given the sheer number of planets and systems. The authors of the paper even conducted a preliminary search. They directed the radio telescope at the Green Bank Observatory to observe 12 planets during their transits. They recorded many signals, but all but 2 of the 2000 were deemed to be interference or noise. Only 2 signals were considered worth further observation, however even these are unlikely to be from aliens. This was only 12 planets observed over a very short period of time. The authors of the paper compiled a list of several hundred potential targets, but there could be many more. I've already mentioned arguments like how we haven't been searching long enough, have explored only a small part of the galaxy, and that our tools are imperfect. What if the problem isn't with tools or with the duration of the search, but with the analysis of the data we receive? Perhaps we've already received signals from aliens many times and just didn't recognize or missed them. With the massive volumes of data today measured in petabytes, traditional classic analysis algorithms might simply not work. And authors of this study, published in Nature Astronomy, proposed analyzing existing data using new algorithms that employ machine learning. They potentially can analyze data faster and provide more accurate results. The authors of the study applied these algorithms to 150 terabytes of data from signals coming from 820 stars. The data were also collected by the Green Bank telescope. And surprisingly, the new algorithms uncovered 8 new intriguing signals in the old data that previous searches had missed. All these signals shared 3 key characteristics. Firstly, all the signals were narrowbands, with a bandwidth of only a few hertz. One of the initial thoughts when encountering a cosmic radio signal is that it might have a natural origin. However, natural signals are usually broad spectrum, though not always. Additionally, the signals have characteristics indicating that their source is accelerating relative to us. This suggests that the source of the signal is not on Earth, as would be the case with a microwave or some terrestrial transmitter. Also, the signals were detected only when the telescope was pointed at a specific source in the sky. If these were terrestrial interference, we would have registered the signal not only from the intended source, but also from other directions. So these signals need to be investigated in more detail, and additionally new analytical methods can be applied more broadly. The authors plan to apply this methodology not to a few hundred stars, but to 1,000,000 stars observed by a Meerkat radio telescope. In this case, the solution to the paradox is not that we have searched inadequately or poorly, rather we haven't even realized what we have already found. Who knows, maybe the massive datasets we have already accumulated contain even more interesting signals. Of course, it might seem strange and unlikely that we are alone in such a vast, possibly infinite universe, and even just within our galaxy. But that's not how science works. Until we have reliable evidence of others, we are alone. However, because new arguments, approaches, and research methods keep emerging, I believe that it's too early to give up. Of course, it would be much easier if they just showed up and said, "Here we are, we exist." The question is, would it end well for us? Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment, and subscribe for more videos in future. Bye.